The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, so for number 2, we're testing another series for convergence or divergence. And we have n equals 1 to infinity of the alternating series of n to the n over n factorial. Alright, so this one seems a little bit complicated, but it's really not. First of all, it's an alternating series, so we either need to check for absolute convergence or conditional convergence. So remember, conditional convergence is that it converges while alternating but does not otherwise. Absolute convergence is this would converge even if the alternating part wasn't there. In both of those though, so let's say we're going to be checking this and the non-alternating version. There's a couple different things that have to hold. Now, in this case, we could use the ratio test, or we could just try to use the test for divergence, which is actually going to work here. Here, on the other hand, if it's an alternating series, remember that in the alternating series test, you actually end up just looking at this part anyway. So anything we do for both is actually going to work here because it's divergent, and I'll show you why that is. So let's write out limit as n goes to infinity of this. This becomes n times n times n infinity amount of times. And n factorial is 1 times 2 times 3 times 4, on and on, as high as you want to go. So what should be clear at this point is as n gets larger and larger, the top starts getting way bigger than the bottom here. Because if you were to stop at some particular n, then these last terms would cancel out. But you'd have an n before this here, but before it on the factorial, you'd have an n minus 1. So you'd have a fraction that's a little bit less than 1. It wouldn't cancel out, or sorry, a little bit greater than 1. It wouldn't cancel out exactly. And you could go on and on down the line until at the first one, I'm grouping these together by the way. At the first one, you have just n, and you have times n over 2, times n over 3, times n over 4, times n over 5, on and on. So as n goes to infinity, this is a product of n's, and its limit is infinity. So remember that by the test for divergence, if you have a series whose limit is not 0, it's automatically divergent. And this limit is clearly not 0. So this is definitely going to be divergent. So let's show that by the ratio test as well. Again, we're going to do the limit as n goes to infinity of a sub n plus 1 over a sub n. So a sub n plus 1 is n plus 1 to the n plus 1 power all over n plus 1 factorial. We multiply by the reciprocal of a sub n, which is n factorial over n to the n power. So let's see what ends up happening here. So these factorials, we have a 1 larger factorial on the bottom and the top. That cancels this out and gets rid of this factorial. So we have that extra n plus 1 left over on the bottom. N plus 1 to the n plus 1 divided by n plus 1, that cancels 1 of that power. If this is n plus 1 to the 1 power, you subtract the powers, 1 of them cancels out. What we're left with is n plus 1 to the n, and we still have this, n to the n. Since they're both now to the n power, we can say that's n plus 1 over n to the n power. And finally, that can be rewritten as 1 plus 1 over n to the nth power. Now remember, we're doing the limit as n goes to infinity. Limit as n goes to infinity of this, that's the definition of the number e. The ratio test only converges if that number is less than 1. E is 2.7-ish, it's definitely greater than 1. So therefore this diverges, again, by the ratio test. If this were to converge even as an alternating series test says that every subsequent term needs to be less than or equal to the one before it, and the limit of the sequence without the alternating part has to be 0. We just showed that's not possible. So this series diverges. It's not absolutely convergent nor conditionally convergent. It diverges straight up due to either just kind of thinking about the limit by test for divergence or doing the ratio test and proving it there.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.